Hello, hello, hello. Hello, Nookus. Hello, Ando Bear. Hello, Amin. Hey, Mike. How are you guys doing today? Muy bien. Doing great, says Amin. How are you doing? I'm doing great. Doing pretty solid. Tres bien. Good afternoon, Jack. Who won the Super Bowl? The Buccaneers, right? Hello, Pika Pika. Tampa Bay. I'm not a huge football fan. I tuned in a little bit. Tom Brady, whose initials are the same as Tampa Bay. Something's going on there. Good afternoon, Trogdur. Good afternoon, D Stratus. Hello, Formula Q1. Americans must be football fans. That's what I've heard. I just never really got into it. Hello, Liam. Gimolino says Brady the GOAT. Hey, Hank. I feel like Brady made some deal with the devil because I just don't think he ever loses. Trogdor, sorry to disappoint you. I'm not a sport person overall. That doesn't disappoint me at all. I'm more into esports, and I'm not even into the popular esports. I'm into like Warcraft 3. I'm getting into chess as an esport. I'm terrible at chess, but I think it's very entertaining. Jack says, this is Buffalo. We're a hockey town. Sabres. Chess is fun. Well, if it's rapid chess, I would say. Nikta, this is our TA. She posted her office hours today. So you'll be able to go to office hours on Discord. That's where my office hours will be also. Bills should have been in the Super Bowl. Come on, Sabres aren't making the playoffs. Hey, you know, we gotta come together. That guy who stinks. Hey, how are you doing? All right. Let's get started, shall we? We're going to talk about Fibonacci's rabbits. And I discussed the rules with you on Friday. You start with 2 rabbits, and then in a month they grow up. And once they're grown up, they make new rabbits. And that takes a month for them to be born, and then they grow, and then they make rabbits. And further, the rabbits never die, and they never stop mating. It's kind of like the trouble with tribbles. If you're into Star Trek. 2047 in total. Wait, at the end of 12 months? I got something different than that. They really need to stop making babies at some point. That's not in this rabbit universe that we've created. They just keep going. All right. So let's go through this. And we're going to come up with a difference equation to describe this process. 986. Are you guys just throwing out numbers? Link 466. I think that is correct. Let's take a peek. So I'm going to make a variable for the population, lowercase p. So let's do p naught for Thanos will come if there's too many. And just snap them. Okay, and so at the end of 1 month, our population is still 2. At the end of 2 months, our population is 4. At the end of 3 months, population is 6. At the end of 4 months, the population is 10. Now, if you look at this, you'll kind of see a pattern emerging. So the population at the end of month 2 is the sum of the previous 2 populations. 2 plus 2 is 4. And you'll see this pattern holds for further stages. Like at the end of month 3, if you add the prior 2 months, that's 6. And then for month 4, 4 plus 6 is 10. Fibonacci sequence with a different base, right? I'm not sure on the exact, I haven't looked at the Fibonacci sequence in a while. I imagine they're the same, given that name. So let's write this out. And we're going to grind through this recursion here. So, oops. P2 is P1 plus P naught. And, P3 is P2 plus P1. It's just the sum of the prior 2. P3 plus P2, which was 10. So, recognizing this, oh, that's the Fibonacci sequence? Oh, okay. So we're just starting with 2 instead of 1, but it's the same rule. Thank you, guys. So we can write a generic difference equation for this, where the population at the end of month K will just be the sum of the populations at the end of the prior 2 months. So we'll tend to use the variable K just to denote a generic step in the sequence. So like I'll refer to K as like the step number. Let's blast through it. P5 is going to be 10 plus 6, it's 16. P6 is going to be 16 plus 10, it's 26. P7 is going to be 26 plus 16, it's 42. P8 is going to be 42 plus 26, and that's 68. These are getting more and more difficult. 68 plus 42 is 110. Okay, so at the end of 10 months, we're going to have 110 plus 68 is 178. At the end of 11 months, and we're almost there, 178 plus 110, which is 288. And our final month, P12, 288 plus 178. And we're at 466, and link gauge nailed it. Okay. So, after 1 year, I mean, that's not too difficult. But what if I asked you 2 years? 3 years? At the end of the rabbit millennia, how many rabbits are we going to have? 1,000 years of rabbit domination with no death and all the rest. That's not a recursion that I want to do. Okay. And also we see that this is kind of growing at an extreme rate. So that's something to keep in the back of your mind. So the question is, as we go to the next page, is there a more sophisticated approach that we can come up with to predict this rabbit population in the following months? And the answer, of course, is yes. There's a better way to do it, and I'm going to show you that today. The answer is that we're going to use the characteristic equation. But before we get into the characteristic equation of Fibonacci's rabbit model, the Fibonacci sequence, we're going to go back to a context where I know you've seen the characteristic equation, and that's dealing with linear differential equations. So the vast majority of you took MAE 340, so we talk about characteristic equations. If you've taken a differential equations course, you've heard the term differential equation before. Belkett says, good old dynamic systems. Yes. So we're going to talk about a characteristic equation and how we use it for differential equations first, because I think this is what you're more familiar with. And then we're going to make the transition to difference equations. Okay, so let's do this example 1. Right here, we have a second order differential equation. You can tell what the order is by the highest derivative that appears. Abel says, shouldn't have thrown my 340 notes out. You guys should keep your notes. I know a lot of people, once they're done with the class, the notes go immediately in the trash. Do you guys do that? Zach says, I have every notebook from every class previously taken. Hey, there you go. I have a lot of notes still. I've thrown out some, but I always go back. You have notes from freshman year. Very nice. Yeah, now that we have like OneNote and stuff, you can store it electronically. That's pretty sweet. All right, let's get into this. So, okay, so here's the differential equation itself. It's second order. Now, on the right-hand side, you see that all these derivatives are equal to 0. That means this equation is homogeneous. So let's go up here and just write what homogeneous means really quick. It means that there's no external influence acting on the system. So if you think about this rabbit problem too, that's a homogeneous problem because the rabbits are just left to themselves. Yes. We have no predators. If I had predators in that model, well, actually that could still be homogeneous. It depends kind of how you set up the system. But homogeneous just generally means there's no external influence. All right, and that's commonly just like a 0 on the right-hand side. And then over here we have initial conditions. You always need a number of initial conditions equal to the order of your system. So this is second order, so I need 2 initial conditions. All right, now the solution of a differential equation is always a combination of its homogeneous part, so I put like a sub H for homogeneous, and the particular part. But you only have a particular solution if you have some external influence acting on the system. So because this system is homogeneous, we don't have an external, so we're just going to have the solution is going to be equal to just the homogeneous part. Now, a homogeneous solution for a linear differential equation always looks like this. Now, you can write out this exponential in different ways. Actually, that'll happen in this example. But for linear differential equations, this is all you really got to remember. The rest you can kind of deduce. So it's some constant times an exponential. So let's say I want to take the first derivative of this homogeneous solution. Well, I'm going to take the first derivative of this right here. You'll see why we're doing this. So like the lambda comes down out in front, and then I have AE to the lambda t. You can do sine and cosine too, right? Yes. Well, because a complex exponential can be represented as sines and cosines. So it all comes back to this. Okay, let's take the second derivative because we're going to need this. We'll just multiply by lambda again. Lambda squared AE to the lambda t. All right, the reason I wanted to do this is because I want to substitute these into our original differential equation up here. So like I start with x double dot. We're going to substitute in this homogeneous x double dot, which is lambda squared AE to the lambda t. And then we're just going to move on to the next term, plus 2 times the first derivative, lambda AE to the lambda t. And then our last term is plus 3 times the 0th derivative, which is just AE to the lambda t. So this equals 0. Now, we can divide the left and right hand sides by AE to the lambda t. Like all these terms share that in common. And this leaves us with the characteristic equation, which is this. Lambda squared plus 2 lambda plus 3 equals 0. We call this the characteristic equation because it tells you the most important characteristics of the system dynamics. So in dynamic systems, we study this equation. We look at the different types of roots you can get. And basically that tells you everything you need to know about a system. How stable it is, if it's a fast or a slow system, whether it oscillates, and so on. So let's get the roots. The roots are just the values of lambda that satisfy the characteristic equation. That's what it means to be a root. And I'm just going to give you those values right here. It's got 2 roots. It's a second order polynomial, so it's going to have 2 solutions. And it's a complex conjugate pair of roots. It's got the real part and it's got the imaginary part. So if we want to write out the solution as a function of time, we come right back to the beginning. I know the solution is a times e to the lambda t. So I'm going to have the homogeneous solution. It's going to be, well, 1 constant times e to, like, let's take the positive conjugate of the root. 1.4142i times t plus a2 e, and then we'll do the negative conjugate. And that is the homogeneous solution. But nobody likes to look at a complex exponential like this because it doesn't really make physical sense. So like what we do is we manipulate this with the Euler identity. And all that does is it turns a complex exponential into a summation of sines and cosines. And what we're going to get is a homogeneous solution looks like this. E to the minus t times some constant C1 cosine 1.4142t. Use Euler. Yep. And this C1 is going to be different than the A1 coefficient, by the way. Like, it's not an accident that I'm changing the variables here. It's going to be something different. And then plus C2 sine 1.4142t. And if you want to fill out the whole solution and solve for these unknown coefficients C1 and C2, how do you do that? Do you remember the secret? Wait, what is that? Oh, use initial conditions. Yes. Because notice the number of coefficients that'll appear here. There's two of them here. And there's going to be, and it's two initial conditions. If I had a third or fourth order system, you would notice 4 unknown variables in there. And you would use the 4 initial conditions. And if you use those, you're going to find out C1 equals 1. C2 is 1 over 1.4142. And then you're done. You've solved this homogeneous solution. Okay. What is the point here? Let's go back to the big picture. Like, why did I go through this? Okay, so here's the point. For a linear differential equation, you can use the characteristic equation. So we'll just like abbreviate this guy to get an explicit expression for x of t as a function of time. Is that an SN next to C2? Flight dynamics student, you nailed it. Thank you. This is a sign with sloppy handwriting where the I and the N have just merged together. Yeah, thank you. So you can use the characteristic equation to get an explicit expression for x of t as a function of time. Meaning, like, now that I have this right here, I can just plug in some value of t, and it gives me back what x is at that time. So this is how we're going to connect it to difference equations, because with Fibonacci's rabbit model, I would love to have some explicit expression where I plug in a step, k, and it just gives me how many rabbits are in the population at that step, k. So I could put in 1,000 months, 2,000 months, whatever. It's not going to be any more work for me because I just have an expression as a function of k. Okay, so here we go. This is what we're going to do next. For a linear difference equation, so not differential, it's going to work a little bit differently, but it's very much the same. You can use the characteristic equation of a difference equation to get an expression for the dependent variable so dependent not in space says figure out when the superior rabbit population surpasses the current human population. Well, that's when it's going to be a problem. So the dependent variable for us is pk. The independent variable is k. Okay, so you can use this characteristic blah 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 to get an expression for the dependent variable pk as a function of the independent variable k. So in the homework, which I just posted, you're going to do this for each of the problems. The solution that we just did on the first page, where we grinded through each month when we added the previous month, that's a recursive solution because it depends on the prior steps, and you have to like keep doing it iteratively. When we use this approach, it's going to give us a non-recursive solution. You can just do boom, one shot, get the answer. Okay, so let's move on to that so you can see what I mean. It is a beautiful thing. If you haven't seen this before, I think many of you probably haven't. I think it's really, really cool. Until I started studying digital control systems a couple years ago, I didn't know about this. Okay, so we're going to go through this same process, but with our difference equation. And so let's start with what we're given. This is our rabbit population model. The current population is the sum of the prior 2 months. So this is a difference equation. You can use it recursively, but we're not going to do that. This is what the homogeneous solution of a difference equation looks like, and it's different than a differential equation. You still have an unknown coefficient, but it's multiplied by lambda to the k. There's no exponential. Can I scroll up for a sec? Boom. What do you need? I'm going to scroll away in like 1 second. Nice. Okay. So notice the homogeneous solution is a little bit different. If you compare to the prior page, it doesn't look the same. All right, so let's see what it would look like for p k minus 1. Well, I just make it to the k minus 1. Do we still call it x sub h and now the variable is k instead of t? Yeah, you could, even though I'm not bothering with the homogeneous and particular subscripts here, I guess you could say this is like pk sub h. This is the homogeneous form. But I'm not going to do that. Okay, and then pk minus 2, lambda k minus 2. So I'm expanding these out because we're going to substitute these expressions into the difference equation. K is just the step. That's right. That's right. Substitute the general form into the, it's not a differential equation, it's a difference. All right, so let's do that. We're going to have a times lambda to the k is equal to a times lambda to the k minus 1 plus a times lambda to the k minus 2. And k equals step, just in a Matlab loop. Yeah, you could think of it that way. That's why these difference equations lend very well to for loops if you're going to do a recursive solution. Let's cancel out these a's. And this is going to get us towards the characteristic equation. So we're going to have lambda k minus 1 plus lambda k minus 2. Let's bring all these terms over to the left-hand side. Lambda k minus lambda k minus 1 minus lambda k minus 2 equals 0. And now we're getting somewhere closer to what looks like a characteristic equation. But I don't want this characteristic equation to be a function of k. Like for a differential equation, the characteristic equation isn't a function of t. So what we do, multiply by lambda. In this case, we're going to multiply it by lambda to the 2 minus k. And depending on the system, you might have to multiply it by something different, but just see what this does. Solve lambda k times lambda 2 minus k. Oops. Minus lambda to the k minus 1 times lambda to the 2 minus k. Lambda k minus 2 lambda to the 2 minus k equals 0. And what this is going to do, this term becomes lambda squared. This one is just minus lambda, and this one is minus 1. Yes, the k's all drop out. So this is our characteristic equation for this difference equation. So just like for a differential equation, you solve for the roots of this characteristic equation, and it's going to tell you all about the system. For example, we know that this rabbit population system should be unstable, meaning that it just grows without bound if left to itself. If we don't go in there and introduce predators, if we don't stand up for the human race and go after these rabbits with pitchforks and whatever, it's going to go out of control. Okay, so let's introduce some Matlab. You guys probably know this. But if you want to get the roots of this equation, it's not too bad to get by yourself because it's quadratic, but we're going to deal with higher order systems. In Matlab, a polynomial destroy their immortality. Yes. You can denote a polynomial like this. You have like the square brackets, and then the coefficient in front of each of these terms, it goes like that. So the highest order term is over here on the left. And if I want to get the roots in Matlab, I use the roots command. So I do roots of that polynomial. All right, let's do that. Let's do it. Roots of 1 minus 1 minus 1. Maybe we'll make this a little bigger. Okay, so we get two roots. It's a second order characteristic equation. All right, write these down. Write these down. Maybe I'll call this lambda 1 is the first one, minus 0.618. Lambda 2 is the second one, 1.618. Is there a situation that for a difference equation where the homogeneous solution will not be of the form that we chose for this problem? Danny, I believe that this form is valid for all linear difference equations. All right. So I wrote down these two roots. Amin says, does the positive root mean that their population growth is unstable? Okay. This root, this positive root, is the reason that it's unstable, but it's for a different reason than you think. It's not just because it's positive. Two negative roots means stable system. for a continuous system. So at the bottom of this page, we're going to talk about this, but for a discrete time system, for a difference equation, you can have positive roots and still be stable. There are different rules. You're going to have to relearn the rules. Okay. Or you don't have to relearn. You just get a new set of rules. Mind is blown, I know. Okay, so let's write out the homogeneous solution. So we're going to have a1 times our first root to the k. So just like we did for a continuous system, you use that general form and you just fill in the roots. Expand some more. We'll continue to expand. We'll continue. All right, let's solve for a1 and a2. Okay. So you use the initial conditions. You use the initial conditions just like you would for a differential equation. So we have the initial population, which was 2. That's one of our initial conditions. So that's going to be a1 minus 0.618, and the k is 0 for that first month. Why is it not lambda to the k minus 1? Well, because I'm using this right here. We are going to have, well, because this is not a, wait, why is not a plug-in for k minus 1? But I'm just plugging in for k. So that's why I don't have k minus 1. Okay, plus a2, 618 to the 0. Pika, you got confused. We can come back to it. If you're still confused at the end of the class, ask me again. Okay, so this is one initial condition. Let's use another one. At the end of population 1, the population was still 2. So we're going to have a1 minus 0.618 to the 1 plus a2 1.618 to the 1. Let's set up like a little matrix here to solve for these. So I have a system of 2 equations. My unknowns are a1 and a2. This is going to be equal to 2. And then this is going to be minus 1, 1, 1.618. Why don't we do this in Matlab really quick? We'll just solve for a1 and a2. You guys probably know how to do this. You've done it before. Let's go over here. So I'm going to say, I'm just going to name this 2 by 2 matrix capital X. Minus 1, 1, minus 0.618, 1.618. Good. And then I'll call the right hand side vector B, which is just 2, 2. So to get those coefficients, I have to multiply that vector by the inverse of that 2 by 2. So I can do it this way. Wait, did I do this wrong? I think I did this wrong. I'm getting different numbers. -1 equals 1. Oh, both the ones should be positive. Oh, I don't know basic math. Oh my goodness. Oh my goodness. Oh my goodness. Okay. Alright, let's do this again. Oh! Okay, thank you guys. Alright, let's go back here real quick. Jeez Louise. This is just one. It's positive one. Oh my goodness. Okay, so anyways. You solve this system of equations. You get A1 is 0.5528. A2 is 1.4472. So this means our homogeneous solution is this. 0.5528 minus 0.618 to the k plus 1.4472 times 1.618 to the k. Now, this is the beauty of this expression. It explicitly gives us the rabbit population at the end of the kth month. And all I have to do is plug in k. I don't have to go through iteration after iteration, summing up previous. So let's try it out. Let's try it out. So let's do P12. Or wait, no, let's do it this way. Let's say K is 12. Let's move it up a little bit. And then we'll say the population is 0.5528 times minus 0.618 to the K plus 1.4472 times 1.618 to the K. Now, do you remember the number we got before? 466. So this is slightly different. I think the reason is that I just don't have all the decimal points here with these numbers. We could enhance it. What if we make K equal to 24? 2 years. Any bets? It went from 2 to 466. Then we start the next generation of the reign of rabbits. Oh my gosh. 150,000 rabbits. Yeah, rabbit stonks to the moon. Diamond hands rabbits. Diamond hands rabbits. Okay. Stonks. So, we found that with some truncation error, whatever, we get back the same answer. Rabbit coin, here we go. So this is a beautiful thing. All right. Let's talk about the difference. Let's talk about the difference in stability criteria for a differential equation versus a difference equation. So, differential equation, we know, because we've taken dynamic systems, it's stable if every root of the characteristic equation has a negative real part. So like, for example, the example we did earlier with the differential equation, we had a second order system and the roots were -1, plus or minus 1.4142i. So because both roots have a negative real part, stable. It's also common to look at stability in terms of the representation of roots in the complex plane. So what I mean is you can plot the imaginary part of the root versus the real part of the root. So for this root, we got like minus 1 plus or minus 1.4142. And using this rule above, this system is, or any linear differential equation is stable if the roots lie in the left half plane. That's what we call it. But that just means that it has a negative real part. Stable, we just call it the left half plane. So if you plot if your system is 100th order, you have 100 roots, one quick way to just get a visual representation of its stability is throw all the roots into the complex plane. And if you see any of them pop up over here, that means the whole system overall is stable because every single root has to have a negative real part. All right, let's talk about difference equations. So this is the difference. Stable if every root of the characteristic equation has magnitude less than 1. This is the stability rule for difference equations. Magnitude less than 1. So let's talk about the complex plane representation because I think this is the easiest way to remember it. You got real, you got imaginary. If the root has a magnitude less than 1, it means that it'll be within a circle with radius 1 if you draw it in the complex plane. So any roots in here are stable. Any roots outside are unstable. So if we do the example of Fibonacci's rabbits, we had two roots. One root was minus 0.618, so it's kind of like over here on the negative real axis. The other root was positive 1.16 or something. So this root is the reason that that system is unstable, but like I said, it's not because it's positive. It's because it falls outside of the unit circle. Because this root could, I mean, if it happened to be negative and over there, the system would still be unstable. So very interesting. There's a difference. Is there a special term if the radius is equal to 1? I mean, I guess you could still call it like a marginally stable system if it lies on that, but it's rare for that case to really come up in practice. The unit circle. Very nice. Very nice. I like that. I've taken 3 controls courses. I didn't know that. Yeah, it's a good one. So it's very interesting. In the coming weeks, we're gonna break down this circle. Is the radius always 1? Yeah, for stability. Yeah, it's never gonna be different than 1. So you might have a difference equation that's higher order. Maybe it's got like 20 different roots. As long as all the roots are in here, unit circle, you're stable. We're going to get some cool shapes, like depending on where you lie in this circle, it changes the natural frequency, the damping ratio. Like we know that there's different rules. Like for continuous systems, like you might remember this. If you have a stable root, the distance from the origin gives you the natural frequency of that root. Like that's a rule for continuous systems. There's a different rule for discrete time systems. So we'll break all that down. Why is it equal to 1? Great question. And it comes back to the solution of the homogeneous form. So think about this. If your root is a number greater than 1, as you increase the number of steps, you're going to have the number greater than 1 to higher and higher powers of k. So what happens to that number? It gets bigger and bigger and bigger. What if the number is less than 1? Like if you have 0.99 to the k, even though that number is close to 1, if you raise it to higher and higher powers, it gets smaller and smaller as you increase k. Now tomorrow, I'm going to post those notes so you can print them out in advance. But we're going to talk about difference equations that have complex roots. It turns out the solution is sinusoidal in that case, even for difference equations. And it's going to be a similar thing where the magnitude of that root is going to be raised to a power k. So even if you have complex roots, you know, so they appear somewhere floating in the circle, the radius, I mean the magnitude of the root, which is its distance from the origin, is still going to dictate the stability. So if I have complex roots out here, it's going to get out of control. What in this example makes their population growth unstable though? There's no predator. Let me tell you what makes it unstable. It's because it's an unrealistic population model, which, boom, they never die. Well, that's number one. And then the fact that there's no predator in this model, that certainly doesn't help. But we can freeze them? Yes. Liquid nitrogen? How did they solve the problem in that Star Trek episode, The Trouble with Tribbles? Do you guys know what I'm talking about? All right, everybody. It's 1:30. So the lecture has officially wrapped up. If you have any other questions, I can take your questions for a couple minutes. Not for too many minutes, because I still haven't had lunch, and I'm going to get hangry. Are these written notes going to be posted to UB Learns? Ooh, I made a note for myself to post the notes today. So those are going to go up today. I'm too Zoomer to understand Star Trek. Are we good to start the homework? Says Amin. So the first homework is up. Let's see, where is this thing? Let's look at it. Okay, you can start the homework. So like, you're gonna be looking at these 4 difference equations, and the first thing you're gonna do is you're gonna get the characteristic equation. So I think at this point, you can get the characteristic equation for all these. You can also determine if these are stable or unstable, because that depends on the magnitude of the root. So if you look at every root and the magnitude is less than 1, then it's stable. If that's not the case, then it's unstable. So you can already do all these. Program a for loop to use the recursive approach. So this is just like what we did at the beginning of lecture today by hand. That's a recursive approach. So make a for loop in Matlab to just grind through the recursion, and that's part 3. All right. Part 4, you can mostly do, I think, because we're going to keep working on this content tomorrow. But this is getting the explicit solution of the difference equation, which is like, where do we go? Where do we go? That means give me this, the solution as a function of k. And I want you to use whatever equation you get there and solve for the solution for like the 20 steps. And I want you to compare the solution at each step to the recursive method. Oh yeah, and then Mike asked, are we going to get feedback on this homework? Yes, the feedback is implicit in this homework because the answer you get for part 4 should match the answer you get in part 3. And that's the way you can check if you're doing this right. If you're getting different answers here, this is the same system. You should be getting the same thing. That's the way you can check. I cannot access the 334 group sign-up sheet. Shoot me an email about that. Sometimes, like, if you use the link from UB Learns, if you just click on the link while you're on UB Learns, it doesn't, sometimes it gives you an error. But if you just copy it, paste it in your browser, it should work. When are the office hours for the week? Let's see. My office hours are today. My office hours are today. They're at... trying to find it. 4 to 5 p.m. on Discord. And then our TA sent an announcement. Her office hours should be posted. To confirm, we only submit the code as part of the PDF file and not the Matlab file? Yeah. So TA hours, Wednesdays 5 to 6 and Saturdays noon to 1. Great. Liam, yes. So I put up an example on UB Learns of what a homework submission should look like. So I think the best way to do it, write it out by hand. Make it really clear, show every step. And then put your code on that PDF as well. The TA office hours are on Discord. All the office hours for this class, Discord. Do I want the .im file? Yeah, I don't need the .im file necessarily, because I think as long as your code is just clearly shown Yeah. Let's see. Yeah, so that's what's going on, my friends. What other questions do you have? Just publish the Matlab file as a PDF and merge it with a written PDF. I think that's a great idea. Yeah, that's a good strategy. Is homework 1 due Friday? Yes, it is. Get started today. Once you get into it, this one's not too bad. How would I access the Discord for this class? I'm having the Discord only open to students enrolled in the course. So, if you're a part of the course, then you'll have the link to the Discord. Yeah, I don't know. Maybe I'll change that policy in the future, but this is what I'm doing right now. Hey, that guy who stinks, thank you. Benny, thank you. Oh, you're enrolled? Oh, then the link is in the syllabus. And if you're on UB Learns, I think I posted the link on UB Learns as well. So it is available to you. Just copy and paste that link, throw it in your browser. Hey, Pika Pika, thank you. Hey, have a great day. All right, everyone. Thank you, Nookus. It's been an absolute pleasure, as always. Thank you. Have a good one, Belkit. Hey, thank you. Glad you enjoyed it. We're going to learn lots of cool things. All right. Talk to you guys later.